go to the last part, which is orientations. Now we have the last piece, which is in Cartesian space, we have to move the end effector, but there are 6 numbers in the end effector. There's position, x, y, z, and there's orientation. The question is, how do we use orientation for the interpolation? Now, we've talked about 3 ways of doing that: Euler angles, rotation matrices, and quaternions. So Euler angles, say there's the initial Euler angle, EI, final Euler angle, EF. What we're going to do is we're going to use a linear time profile. Okay, and then I'll show you how to do it with cubic and quintic, but let's take a linear profile. Here I'm going to rescale the time. So t minus ti, tf minus ti. And the reason I do this is because if I put t equals ti, I get t prime is 0. And if I put t equals tf, I get t prime equals 1. So it just rescales it from 0 to 1. It's easier to work with that. And you could do that for the earlier ones too. Just that here I'm doing it and there I did not do it. So we can interpolate the Euler angles as 1 minus t prime ei plus t prime ef. Okay, simple formula, linear interpolation. You'll do this for each of these values. So you do this for phi, this formula. So you get phi I. So phi as a function of t prime, theta as a function of t prime, and psi as a function of t prime. The issue is the same thing we've seen before. There could be a gimbal lock. For the 1 to 3, the gimbal lock occurs when theta is pi divided by 2. And I'll show you how that happens in a bit in the code. There's could be discontinuities because what happens is angle, it goes from 0 to pi. After that, the angle gives the same sines and cosines. So there'll be a angle wrapping happening at 360 degrees. And this is one of the biggest problems. It may not give the shortest path. So this I'll come to you at this point a little bit later. So this is one way, and I'll show you how to do this using code, and we'll see the problems with that. The second way of doing this is rotation matrices. Okay, so rotation matrices, start rotation matrix, end rotation matrix, rescale time. We have, this is the formula for r as a function of t prime. Okay. Now, there's a problem with this kind of interpolation. Remember that rotation matrix is orthogonal, which is R transpose R. And just making an interpolation this way does not let you keep R t prime as orthonormal, which is if you take R at any time, it will not be follow this. So what you need to do in order to make R orthonormal is you do the singular value decomposition. This is one way in which you can get the scaling parameter out. Don't worry too much about it. But what these terms, U, S, V, is basically are is that you can write the rotation matrix as U times S times V transpose, where U and V are orthonormal matrices, and S is a diagonal matrix, so it will only have diagonal terms, and it actually has the length parameter to it. So the length is hidden in S. In order to make R transpose R equals that every time step, what you do is you essentially strip off the S. So here, to make R orthonormal, we just strip off the S. So you can see it over here. Go back. Note that this was the formula. And there was this S, which is the scaling parameter. It basically is the sort of the length scale. We just stripped off the S totally. So we removed the S. So we now have the R as this, but U and V are orthonormal matrices. So they will follow the property that R transpose R is I. Now there's another problem with this though. You need to check the determinant of R. And if the determinant will be determinant of U, V transpose. Sometimes the determinant is -1. Okay, now determinant of -1 means that you're not using a right-handed system, you're using a left-handed system. We don't want to use left-handed system. So what we do is to make determinant R equals 1, we simply flip the sign of the last column of U. Okay, really, you can flip any column, doesn't have to be the last one. So once you flip, so every column, every element in the column is multiplied by -1. And then once 1 and 2 are done, we have So once they are done at every interpolation step, we have R transpose R equals I. Now, this is the problem again. This particular method of rotation matrices interpolation may not give the shortest path. Again, I'll talk to that just a bit once we get the Quaternions. Finally, we come to the Quaternions. So Quaternions, same way, the initial Quaternion, final Quaternion, these are 4 cross 1 vectors, the 4 elements. You do the same thing with Quaternions, same formula. There's going to be one issue though, which is you will not, this doesn't ensure that the modulus or the norm is 1, because who knows what happens when you take individual elements and interpolate, right? So this is fixed at every time step by just taking the Q and then this normalizing. So this is what you would. So this Q is here and here, and this is the new Q, which comes from normalizing. Now, there's an issue with this, which I'll talk about in a bit detail. It leads to non-constant angular velocity. It's not really an issue right now when we're doing trajectory generation because we're not using dynamics, but you'll see that the velocity is non-constant. And that is an issue. Earlier, if you looked at, we talked about having time profiles with velocity starting at 0 and ending 0. This one will have non-constant velocity. So they'll see a jump in the velocity, angular velocity, actually. The issue with this is that and I'll come to this, leads to non-constant angular velocity. Why that's important? Well, if you see this Q, if you take the derivative of this Q and you get the the Quaternion dot, you expected that this is supposed to be constant, right? Because it's a linear function of time. But when you actually compute the angular velocity, which is different from the Quaternion dot, you will see that it is non-constant. There's a relation between omega and Q, right? It is like Q dot Q bar. And forgetting the exact, there's one for body frame and there's one for, let me see if I can find it. It is Q, that's right. And then body frame, it is Q dot, sorry, rather 2. So 2 here, and then there's a 2 Q bar dot. So you can find the angular velocity by using this relation. Q dot is constant. Why it's a constant? Because Q is a linear function of time, so Q dot is constant. But omega turns out is not constant. And you can see why that's true, because it's function of Q dot and Q conjugate, which is just taking the non-constant part and negating it. So that will be a linear function. So omega is expected to be a linear function. So that's another issue. If you look at Quaternions, it's a constant, and then there is Q1, Q2, Q3, such that Q0 square plus Q1 square plus Q2 square plus Q3 square equals 1. Okay, so that thing is a constraint. Okay, similar to example would be this. We have x, y, and x square plus y square equals, let's say 1. So this is basically a unit circle. Right? So this thing is going to be, it's very hard to draw something like this on the left side because you have 4 parameters, Q0, Q1, Q2. So you cannot draw 4-dimensional, it's not a sphere because sphere has 3, right? This is 4. So in 4-dimensional space, whatever that space is, this thing is going to be a 4D sphere. And it needs to ensure that it lies on the 4D sphere, right? And that's basically this whole step of making Q equals 1. So this path on the 4D sphere, it's going to be about time, will stop. This is a geodesic path. Okay, so when you're trying to traverse on the sphere, you need to take a path on that sphere which respects this coordinate, this particular equation. Okay, this is not the same as Euclidean path. in two-dimensional space, when you want to go from point A to point B, you really don't have any constraint. You could go anyway. Right? You could just do anything. So we did quintake, fifth, it doesn't matter. But for something to maintain orientation, there is certain relation you need to follow, and that orientation should always follow this path. And because of this, you don't see that Euler angles and rotation matrix are able to do this because they don't really follow that path. So that actually gets us to, in fact, also the interpolation, linear interpolation, which I talked about, does not follow the geodesic path because you need to normalize it. So all those three methods have the problem that they do not follow this shortest path on the 4D sphere.